Welcome to the next lecture of information theory and coding. In the previous lecture, we have discussed some of the characteristics, and hopefully we have noted down some 5-6 characteristics of an source coding algorithm. So we can consider all the code as a proper code or proper source code. So every source code should have some of the properties which we have discussed. And today we are going to see one source coding, or that is called the Shannon's coding theorem. So Shannon, as per the Shannon's coding, the length of each code is given by that is represented by small l. So that is equal to log base 2 1 divided by the probability, that is p. So if a source is generating some set of symbols with some of the probabilities, for example, I will consider that a source is generating some certain number of symbol. So the symbol, the ith symbol is having length li, that is equal to log base 2 1 divided by pi, where pi represents the length, the probability of ith symbol. And when we calculate the length using this expression, and we are getting a value of length that is some decimal. Suppose after calculating, I will get the value of li, that is equal to 1.2. So Shannon has stated that if the value of li is a decimal value, then you approximate it to the next integer value. So that after 1.2, the next integer value will be 2. So you can take the li as equal to 2. And in that case, we can write that log base 2 1 divided by pi. This is less than or equal to li, which is less than or equal to 1 plus log base 2 1 divided by pi. So this is the relationship has been given by Shannon, and what it tells, if we talk about the statement, the value of li should be the, if the value of li you are getting a decimal, in that case you approximate that decimal value to the next integer. That does not mean the value of li will become 3. Okay, because 3 is not the next integer. Okay, so this is a wrong decision by taking the value of li is equal to 3. So after 1.2, what is the value, and that value should be an integer value that you can take as the value of li, and it happens only when you are getting a decimal value or li, which has been also expressed by Shannon's in a different manner. Suppose I am getting this value is equal to 1.2 as per my representation over here. So what I said that we have to approximate to the next integer. So this is nothing but the 2. And that equals, when I mention 1 plus log base 2 1 divided by pi. So this value we obtain 1.2. So 1.2 plus 1 is equal to 2.2. Okay. So this is other way of finding the value of li. So when we approximate, or when we take the value of li as an integer value, so that value should be greater than the exact value of the logarithm, the exact value of log base 2 1 plus pi, and that should be less than 1 plus log base to 1 by pi. So 1 plus log base to 1 by pi is equal to 2.2. So that is why I said now we cannot take 3 here, because if we are taking 3 here, so 3 is not less than 2.2. Okay, so this is another way of expressing the ideal value of Li. So what Li represents? Li is the length of ith code word. So suppose if source is there which is generating some symbols such as S1, S2, S3, so on, like n number of symbols the source is generating. So L3 represents the length of ith code word, because Shannon told that in coding we convert all the symbols, or we convert all alphabet, or we also convert every message signal by a sequence of code having some sort of length. So that is called the code word. Okay, so when we convert every message, every symbol into a sequence or a code sequence, what is the length of that code word? So that is represented by small l. That means the symbol S1 will have the length L1, this has the length L2, this one L3, so on, like that. The last symbol will have length Ln. So the value of small l can be different for different symbols. But if we have to calculate what is the average length of the source, because the source is generating multiple symbols, and each individual symbol, when encoded, each code word of respective symbol are having different length. So if someone asks what is the average length of the source, that means what is the average length for symbol the source is generating. So that we represent by a symbol that is capital L. So capital L is the summation I is equal to 1 to n, where n represents the number of symbol the source is generating. That summation is pi into Li. So this Li is the small li. So probability of every individual symbol multiplied by the length of every individual symbol. So once we sum up this, we will get the average length of the symbol. Okay, so always the average length is greater than or equal to HR of S. Okay, where HR of S is equal to H of S divided by log base 2 R. So what does mean by that? If we take the binary, that means the coding is a binary coding, so R value is equal to 2, and in that case log base to 2, this will become log base to 2 is 1. So we can write HR of S is equal to H of S. All right. Now, if we find the H of S, so H of S, we know that represents the average information, or that is called the entropy, which we can express by the summation I is equal to 1 to n probability of I log base 2 1 divided by probability of I, and having the unit bits per symbol. And we have the expression of L. From this we can find the coding efficiency. So this eta subscript C represents coding efficiency. So this we can find as the ratio of average information with respect to the average length. Okay, and from this we also can derive another term that is called the coding redundancy, which is equal to 1 minus coding efficiency, where both the terms coding efficiency and coding redundancy, they are expressed in percentage. All right, so now let us take an example and let us find out all the parameters. So let me take an example. Okay, so see this example. A source emits an independent sequence. So first of all, very important information it has given in the question: independent sequence. Okay, so the symbols are independent. So if it is independent, that means we cannot apply the Markov process. It is emitting an independent sequence of symbols from an alphabet consisting of 5 symbols A, B, C, D, E with probabilities 1 by 4, 1 by 8, 1 by 8, 3 by 16 and 5 by 16 respectively. That implies the symbol is transmitted at a probability 1 by 4. The symbol B is transmitted at a probability 1 by 8. The symbol C is transmitted at a probability same 1 by 8. The symbol D is transmitted at a probability 3 by 16. And finally, the last symbol E is transmitted at a probability 5 by 16. Question is to find the Shannon's binary code for each symbol and then find efficiency of the coding scheme. So I will try to find out what the coding representation of each given alphabets A, B, C, D, and E. So when we apply coding Shannon's encoding, so how the alphabet A will be encoded, how the alphabet B will be encoded, and C will be encoded, and if alphabet A will be encoded, what will be the length of the binary code for alphabet A, what will be the length of binary code for alphabet B, so on we will see by solving this example. So the step-by-step procedure of in solving this example, I will explain you, and I request to you to follow the step-by-step process of solving this example. So as per Shannon's, what we will do, we have to arrange these probabilities in their descending order. That means we have to write down which symbol is of high probability. So you see it is 1 by 4. This 1 by 4 I can write it as 4 by 16. This one I can write 2 by 16. This one I can write 2 by 16. This one itself 3 by 16. This one itself 5 by 16. So I have made all probabilities as equal denominators so that it will be very easy to find out which probability is highest. So if you see here, this probability 5 by 6 is highest. So 5 by 6 that represents symbol E. So E symbol having probability 5 by 6, 5 by 16 is the highest probability. So that I will write first. The next highest probability will be 4 by 16, which is for symbol A, that is 4 by 16. Next highest probability is 3 by 16, that is for probability symbol D, 3 by 16. Next, there are two probabilities which are equal for B and C. So you can write anyone first, anyone second. There is no issue at this stage. Okay, so once the first step is to arrange the probability in their descending order. The next you have to find out a parameter that is called alpha I. So we have to calculate the value of alpha I for E, for A, for D, for B, as well as for C. So first of all, here I have 5 different symbols. So the value of I should go from I1, I2, I3, I4, I5. So the first value of alpha I, that is called the I1, that you have to take by default 0. Always remember the first value you have to take as 0. And the next value of alpha I, that is called alpha 2, that you can find out by summation of these two, what you are getting. 0 plus 5 by 16, you will get 5 by 16. Similarly, alpha 3 we can obtain by taking the summation of this as well as this probability. So it will be 9 by 16. So this will give us the result 9 by 16. And hence the alpha 4 is the summation of 9 by 16, 3 by 16, that is 12 by 16. Okay, this summation, the result you will write here. Similarly, alpha 5 will be the summation of these two, and the result you have to write, that is 14 by 16. These are the values of alpha I. So to remember that, first you have to take by default 0, and next you have to calculate by adding alpha 0 with P0. Then you write here, sorry, alpha 1 plus P1, then you write here. Then alpha 2 plus P2, you write here. Then alpha 3 plus P3, you write here. So on, you will keep on doing, and you can find the alpha 5 value at the end. Then next to calculate small li value. And I told you in the very beginning that small li, we represent small li as log base to 1 divided by pi. So what is your small li? That is log base to 1 divided by pi. Okay. And when we calculate the value of small li, as per Shannon's, this should be an integer. If we are getting a decimal value, then we have to approximate that decimal value to the next integer value. So here you see what is the probability you are getting, 15 by 16. So log base 2 1 by 5 by, sorry, 1 divided by probability. So probability is 5 by 16. So that is equal to log base 2 16 divided by 5. Okay. So if you calculate this, you will get this value is equal to 1.67. So 1.67 itself a decimal value, which we can approximate to next integer value, that is 2. So this one will be 2. Okay, so we are taking the probability. We are not taking alpha. We are taking the probability. Similarly, for second, log base 2 1 divided by probability. Probability is here 4 by 16. So 4 by 16. That is log base 2 16 by 4. So 16 by 4 is 4. So log base to 4 is 2. So again, the value will be 2. Next one, log base 2 1 divided by probability, that is 16 by 3. Directly I am writing now 3 by 16. So it will be 16 by 3. So 16 by 3, it will be 2.41. So that you have to approximate to 3. Next integer is 3. Similarly, log base 2 16 by 2, because it is 2 by 16. So 1 by that will become 16 by 2. So this will become log base to 8, that is equal to 3. So it is directly coming as integer value. So we don't have to approximate to anything, because at itself the result is an integer. Directly you can write 3. Then the last one, again 2 by 16, definitely it will come 3. So in this way, what we have obtained, small li. Small li is what? You recall what I had written, small li. Small li is the length of ith code word. Okay, so that means in this example, when we represent the alphabet E by a code word, so that code word must have a length of 2 bit. Similarly, if the alphabet A will be encoded by Shannon, then that code word will have a length of 2 bit. And the alphabet D, when will be encoded, then that code word will have a length of 3 bit. So that is the meaning of small li. That small li represents what is the length of the code word. All right. Then next, what we will find out, the binary representation of alpha I. Okay, so binary representation of alpha I. The value of alpha I, see all the values of alpha I, these are decimal representation. Okay, so 0, the value is decimal value is 0. If you convert it into binary, then it will become 0 0 0 0. Similarly, 5 by 16. Okay, so what is 5 by 16? If you use calculator, what the value you will get? 5 by 16 is equal to how much? It will be 0.31. 0.3125. This ratio, by simply using calculator, this ratio is 0.3125. Okay, so this is a decimal number in number system. This is a decimal number system. You have to convert that decimal number system into binary number system. How we can do? See, the integer is 0. Only the decimal parts are 3125. Okay, so 0.3125. So you have to multiply it by 0. So it will be 0. Then it will be 2 into 2 plus 1 5. 2 into 1 2. Then 2 into 3 6. Okay, so 0 point this. So integer value is 0. So you note down the integer value. Again, you multiply this by 2. So it will be 0, 2 into 5, 10. So 1 will come, 2 into 2 plus 1, it will be 5. 2 into 6 is 12. So 2 will be here, 1 will come here. So the integer value here is 1. Okay. So now again you multiply by 2. So when we multiply, do not consider the integer value. You just multiply the decimal value. So 25, it will be 0.50. Only we have to multiply to decimal value. So again, what is the integer here? 0. And you multiply by 2. And up to what you will keep on multiplying when all the decimal positions have become 0, 0, 0, 0. Till that you will keep on multiplying like this. Okay, so it will be 1.00. So your all decimal places are 0. So you stop here. So integer is 1. So note down the integer. So what you got 0, you have to write from top to bottom. So 1 0 0, sorry 0 1 0 1. This one is 0 1 0 1. And since it is a decimal value, you can write 0.0101. Okay, so this is the basic thing, how to convert a decimal number system into binary number system. And I explain it for this one. Similarly, you can do for other thing. And once you do it, what values I have received are 0.1000. This one will be 0.1100 and last one will be 0.1110. Then a general question is why I have taken the decimal value up to 4th position. Why not 5th position? Why not 3rd position? And why not 2nd position? Okay, the answer is each code word is having here length 2, here length 2, here length 3, here 3, and here 3. So the maximum length is 3. So you can take this decimal value up to a maximum length of 3. But it should not be less than 3. Or if you are taking any length which is higher than 3, then there is no issue. But if you are taking any length which is less than 3, then you will face difficulty or your answer will come down. You see here why your answer will be wrong. So this is the binary representation of your alpha I. And finally, what is the code? What is the code? Since the length is 2-bit, you just take only 2. Only 2-bit you take. Okay, so that is 0, 0. And one thing, since here everything we are writing 0 point something, you also, if you want, you can write here also 0 point. No issue. Okay, so you take 2-bit. Here length is 2, so you have to take 2-bit. So that is 0, 1. But here length is 3, so you have to take 3-bit, that is 1, 0, 0. Here length is 3, so you have to take 3-bit, 1, 1, 0. Here length is 3, so you have to take 1, 1, 1. So finally what happens when we encode the symbols which is generated from a source, and the symbols are the alphabets like A, B, C, D, E. So after encoding, the E will be represented by a code word 00. A will be represented by a code word 01. So on, the D will be 100, B will be 110, and C will be 111. So these are what I explained are different steps in order to represent or in order to apply coding or Shannon's coding algorithm to any particular source generating some number of symbols with different probabilities. Now, coming back to the question, we have obtained the Shannon's binary code for each symbol. The next part is to find out the efficiency of the coding scheme. And we know the efficiency of the coding scheme is the ratio of the average information to the average length of the symbol. And average information or entropy, it can be obtained from the summation of I is equal to 1 to, here you have how many symbols? 5 symbols. So I is equal to 1 to 5 pi into log base to 1 by pi. This will give us the average information. And in order to calculate the value of average length of the code word, you have to take the summation I is equal to 1 to 5 pi into small li. Okay, in order to calculate the capital Li, you take the summation of product of pi into small li. So these formulas we will use to calculate the code efficiency. So what will be the value of capital L? So capital L is what? Average length of symbol. This is capital L. What is small l? Small l is not the average. Small l is the exact length of the symbol. For example, here in this table of small l, you can see L1 is equal to 2. That means the code is having length 2. L2 is equal to 2. So the code is having length 2. L3 is equal to 3. So the code is having length 3. Got my point? So how we can calculate the L? That is summation of I is equal to 1 to 5 pi into small li. So that is equal to P1 small l1 plus P2 small l2 plus P3 small l3 plus P4 small l4 plus P5 small l5. So all probabilities are given. P1 is how much? You can write this one. This probability 5 by 16 into L1 is 2. So 5 by 16 into 2 plus next probability is 4 by 16 into length is 2. You see here 4 by 16 and length is 2. This one. Then 3 by 16 into 3 plus 3 by 16 into 3 and next one is 2 by 16 into 3 plus 2 by 16 into. So this result is 2.4375. 2.4375. So what is the unit? Unit is bits per symbol. So this is what we obtain. We obtain the average length. That means when the source is generating 5 different symbols such as A, B, C, D, E, and after that when we apply the Shannon's coding, then all symbols are not having equal length. Some symbols are having length 2 bit, some symbols are having length 3 bit, so on like that. So if in an average, if it will be asked what is the length of the code word per symbol, then the average length of the source is 2.4. So 2.4 bits per symbol in an average is the length of code word. Okay. Now we calculate what is the average information or entropy of the source. So this is our previously conventional formula. So that is pi log base to 1 by pi. So this we can expand p1 log base to 1 by p1 plus P2 log base 2 1 by P2 plus P3, P4 like this you can write, and it will go up to what? P5 log base 2 1 by P5. Okay. So P1, P2, P3, P4, P5, all values are given over here. So only you use the value and calculate. And if you do this calculation, you will get the value of HS that is equal to 2.2272. 2.2272, and the unit is again same, bits per symbol. So what is the coding efficiencies then? That is the average information divided by average length, 2.2272 divided by this one, 2.4375. So this result is 0.9137. And if you calculate, if you want to find out the efficiency or the code efficiency in percentage, then you have to multiply by 100. That will be 91.37. And if you want to find out what is the code redundancy, then it will be 1 minus code efficiency. So that will become 8.63. All right, is it clear? Now, let me modify this question. This particular question I will modify. If it is asked to find out what will be the Shannon's code and what will be the coding efficiency of the second extension of the source. Okay, we will find the second extension of this source. So second extension means what? How many symbols we will have? Here how many symbols? 5 symbols. So 5 symbols are there, and second extension. So 5 to the power 2. So 5 to the power 2 will be 25. So we will have a total of 25 symbols after the second extension of the source. So what are those symbols? So one symbol we can write one symbol as A, AB, AC, AD, AE. Next one is BA, BB, BC, BD, BE. Then CA, CB, CC, CD, CE. DA, DB, DC, DD, DE. EA, EB, EC, ED, EE. If you calculate what we are getting all total, we are having 25 number of symbols or 25 number of alphabets which are generated by the source after second extension. And we also can find out what is the respective probability of this symbol which we have represented by AA. So how we can do it? You see here the symbol A is having probability 4 by 16. Okay, so 4 by 16 means 1 by 4. So A is having probability 1 by 4. So 1 by 4, this A is also having 1 by 4. So 1 by 4, 1 by 4, if you multiply, you will get 1 by 16. Similarly, the second symbol AB, what will be the probability? You see here, A is having probability 1/4, B is having 1/8. So AB will have probability 1/4 multiplied 1/8. So 1/32. So this will be 1/32. So unlike that, you can calculate what is the probability of all the symbols, all 25 number of symbols which are generated by the source after second extension. All probabilities you can find out. Then you follow the same process. That means you arrange the probabilities. You arrange all probabilities in the descending order, and you keep on calculating the value of alpha, and then you calculate the value of Li. Then what will be the binary code and what will be the code. Using the same process, you can do it. Once that part is over, you can go for finding the value of capital L, that is the average length of the symbol transmitted by the source, and we have to calculate HS. So how here you see, when we are calculating for second extension, what will be the formula? What is the upper limit of this I? It will be 25, because now you have 25 symbols. Okay, pi into small li. So pi you have calculated here. These are the pi's. This is pi. This is pi, and you have calculated pi. And similarly, li also you might have calculated. So that will give us the L value. And next, when you are going to calculate H of S or the entropy, okay, you just recall our previous discussion of entropy. When we are finding the second extension of entropy, that we represent as H of S square, that is nothing but 2 into H of S. We had a property studied before that if we are finding the nth extension of any symbol, so the entropy of nth extension is nothing but the n times of the entropy of first extension. So once you have calculated the value of HS, for the second extension, you don't have to calculate or don't have to go for these processes. You simply multiply this by 2. That will give us 2 into H of S you do. That will give us H of S square. And then we can calculate the code efficiency, that is H of S square divided by L. So that will give us the coding efficiency. So this is the example I have shown you, and particularly what I have shown here, there is a problem related to this particular case. That means when when we are calculating the second extension, based on that one problem is there. So we can take up all those problems and try to solve, because I have shown you the process or the hints when we are doing for the second extension how to calculate. So you can take up and you can try to solve this. Okay, so with this we have completed the Shannon's channel coding algorithm. And if you have any question or any doubt, so let me know it so that we can discuss here.